Hey gang, let's talk about polarization. When I think about polarization, I think about political parties, right? How the left and the right have become more polarized, more separate from each other. Or I think about the North and South Pole. You can't get any farther away on the planet than if you are positioned at one of those two locations. Or I think about these sunglasses that fishermen, for example, have been wearing for years. Why? Because these polarized sunglasses are able to take the horizontal light waves that come in off of reflected surfaces like water and are able to block them, reducing glare, while still allowing the vertical wavelengths that allow me to penetrate into viewing the water to be seen. Really handy when I'm driving, too. So let's talk about the same idea of polarization as it applies to wireless, as it applies to RF signals. Now, what we find is that when I have, a particular wireless antenna, it's going to be configured in a certain way to send out a pulse, an electromagnetic pulse, a waveform that is going to generate from the antenna starting point and go out into the air. But it isn't just in any random direction. There's a particular shape that it has, dictated by the antenna. What we find is that the waveforms that are associated with our RF signals are going to be polarized. In other words, they have a distinctive orientation. There's a difference between north and south. There's a difference between left and right. There's a difference between a vertical wave and a horizontal wave. And there's also another type of polarization called a circular polarization that actually moves around a center axis. But the type of polarization that we typically see with wireless is actually this one right here, a vertical polarization loop. That's typically used. Actually, television signals were originally given a horizontal axis, so Wi-Fi was given a vertical axis so that they wouldn't affect each other that much, even though there's some overlap in terms of where those ranges might touch each other. So Wi-Fi typically uses a vertical polarization for its electric wave, right, for the electro aspect of it. Now, what's interesting is that although the waveform is polarized vertically, there's a magnetic field, right? We talk about it being an electromagnetic pulse, an electromagnetic field. That electromagnetic pulse means that it has both, and magnets, you've worked with magnets, right? You know the way that the north and the south kind of line up to each other. They have a certain orientation that always fits them together. And when we have an electromagnetic wave, we'll have the electric aspect of the wave dictated by the antenna following this vertical orientation, right? So that's the vertical wave. The magnetic wave follows right along with it. It's perfectly in tandem, but 90 degrees to the left. All right. So if the wave is rising up of the electrical current, the magnetic wave is moving in a leftward fashion as we look at it here. So that's this orientation following along. As it dips down, then it goes to the right and back and forth. So that follows right along, and it is the combination of those two things that is actually the full waveform that is being sent from one antenna to another as we're moving along here. Now, that happens because of the antenna. Let me bring out this antenna again. This antenna, right, is designed to be a remote antenna that we can put to an access point. If I were to take this antenna and let's say I were to mount it to a wall, I might think to myself, okay, well, all of the people that are going to be receiving this signal are that way. So good, the antenna's pointing that way, right? No. The antenna has a particular orientation that the manufacturer dictates. Now, typically, and this is the case here, that means we want these antennae to be up. So if I'm mounting it to a wall, that means I need to orient these vertically. If I'm positioning this flat on a base surface, that means the antenna need to come up like this. So I need to make sure that the orientation is done correctly so that this waveform can be sent out correctly. If the waveform is not sent out correctly, then if I have a sending antenna and a receiving antenna, and the sending is like this and the receiving is like this, gang, it's like polarized sunglasses. I'm missing out on a lot of the incoming signal, just like the polarized sunglasses do that on purpose. Misaligned antenna will cause that same thing to happen with our RF signal. And when that happens, you lose up to 20 decibels of the strength of that signal. That's 100 times less signal coming in just because you tweaked your antenna in the wrong direction. So follow the manufacturer's instructions. This is why orientation of antenna is so important. Polarization and the magnetic field.